Hello. Now we will calculate the capacitance of a parallel plate capacitor when the dielectric is placed in between the capacitor. So this is our parallel plate capacitor, and inside this parallel plate capacitor, a dielectric of dielectric constant K is placed. The dimensions, the cross section area is A, and the distance between the parallel plates are D. So they are almost touching each other. So since there are two plates we see, so one plate will give the charge plus Q and other plate, second plate will give the charge minus Q. Net charge remains 0. So as we all know that the value of electric field decreases when the electric field goes inside the dielectric due to the polarization of the dielectric. So when the electric field will go inside due to the polarization of charge across the edges of dielectric, the value of electric field inside the dielectric will decrease. So at any general point, if I want to calculate the electric field due to the positive charge, it will be away from the positive charge, and due to the negative charge, it will be towards the negative charge. So both are in the same direction. Okay. So sigma for the plate, the surface charge density for the plate will mean Q by A. And we have the formula to calculate the E1 as well as E2. Similarly, since dimension wise, the dimensions of D is very less compared to the dimensions of A. In that case, we can assume for all points inside the dielectric, these plates are of the dimension of infinite dimension. So they are very large plates since these plates are very nearby. So when these plates are very nearby, then for all points, these plates will look like they are of infinite dimension. And we know the formula for electric field, due to the infinite dimension plate. And that formula is sigma upon 2 epsilon naught. This is the formula in case of air or vacuum. Since we are calculating the electric field inside a dielectric, the field will be epsilon naught K. So this is inside dielectric in this case. Now, the E1 as well as E2 both are same magnitude wise because distance is very small. So we can calculate the net field at point P, and that will be the summation of both the fields, and that will be equals to this 2 times of this value. So 2 sigma upon 2 epsilon naught K, and that becomes sigma upon epsilon naught K. So field at point P becomes Q by A epsilon naught K. Now, if you can see the formula, in this formula, electric field comes out to be constant. And for the constant electric field, we know the relationship between the field and the potential difference. So the V1 minus V2 divided by D is equals to E. That's the formula. Voltage between 2 points divided by distance between the 2 points is equals to electric field. But that formula is only valid when this electric field is constant, not for variable electric field, only for constant electric field. And we already know since there is a positive charge onto plate 1 and there is a negative charge onto the plate 1. So potential at plate 1 will be maximum and the potential at plate 2 will be minimum. So the V1 will be max and V2 will be minimum. So let's calculate. So V max minus V minimum divided by D is equals to E, which is having the value Q upon A epsilon naught times of K. And in case of capacitance, V max minus V minimum, we combinedly write this as V. So V upon D is equals to Q by A epsilon naught K. Upon rearranging, Q upon V will be equals to A epsilon naught K by D. So we get the ratio of Q by V. Now let's compare this formula with standard equation, and that is Q by V is equals to C. So if I compare these two formulas, the value of C will be A epsilon naught K by D. So this is the capacitance for a capacitor in which there is a dielectric. Dielectric is completely occupying the capacitor. So A epsilon naught K by D. So you see, this is different than the previous formula. When the dielectric is not there, the formula was A epsilon naught upon D. This is with dielectric. With dielectric. And without dielectric, the capacitance was A epsilon naught upon D. This was without dielectric. This was without dielectric. So if you see, there is only the difference of this. So in case when you place the dielectric, this epsilon naught gets converted into the epsilon naught K. And epsilon naught K, this epsilon naught K is the permittivity of the medium between those two. So since we already know the epsilon is equals to epsilon naught times of K in case of dielectric, this is the dielectric constant of the dielectric and this is the permittivity of dielectric. Of medium in which the dielectric is there. So basically, as you can see, this is the general formula. This can be a general formula. In this general formula, all you have to do, this epsilon naught should be the permittivity of the medium in the capacitor. If the medium is vacuum, you will write the permittivity of vacuum. If the medium is a dielectric, you will write the permittivity of the dielectric, which is this. And the value of this can be written as epsilon naught times of K. Okay, so this is the formula. Now, as we have already seen, if you want to have the large value of C, this A by D should be very large. One more thing, now we have this value of K. So, if the value of K is large, then C will be large too. So, if you want to have the more and more capacitance, you have to use the larger value of dielectric constant, and the largest value can be infinity, but the problem is if the value of K becomes infinity, which is in the case of conductors. So if in case of dielectric, if you use the conductor, you will be having the largest value of K, and that will show you that C is infinity, but that's not the case. Because you see, if you use the conductor, this charge will move to the negative plate and the charge distribution will vanish, and that will end the electric field. So whatever K, the K value should be large. But that K value, for that K value, the conductivity should not be there. So dielectric constant should be high, but the conductivity should not be there. That kind of dielectric you have to use. It should be dielectric, not the conductor. So if you want to have them large, now there are some things. If you want to have large value of C, the value of A by D should be very large, or you can say the D by A should be very small. Along with that, you have to use the dielectric for a larger value of K.